Okay, so we are going to start with our capture question. And our capture question says, do you think a star spends its entire life in one place on the HR diagram? That is a reminder of what we did on Monday together, which was our HR diagram. We said that our sun is somewhere in this general area. Is it going to spend its entire lifetime still in that general area? So what do we think? Somebody help me out. Do we think the star is going to spend its entire life in just one place of the HR diagram? Lizzie?
I don't think so, because isn't it more elements it fuses, the bigger it'll get?
Oh, so she's saying that as it ages, it's going to be fusing different elements in its core. I would agree with that. So it's going to look different. It will also, as it ages, change in characteristic. It will start swelling up and it'll become a red giant as it goes into old age. So, do you think a star spends its entire life in one place? The answer is no. Let's go ahead and talk about our sun. Our sun is currently in the main sequence. Is yours still loading? The main sequence of the HR diagram. As it ages, it will swell and turn red. This makes it a red giant. After it goes red giant, it's going to then, the next star will be a white dwarf. Then it will eventually cool and become a black dwarf. Now, we believe that black dwarfs will actually happen. We're theorizing it, but black dwarfs will it'll be in its white dwarf stage for trillions of years. Our universe is only 13 billion years old. So we have not really ever seen a white dwarf cool off to become a black dwarf. White dwarfs you could think of as being like if you have a campfire and the fire's no longer burning, but you know those coals are still glowing in the bottom of a campfire? That would be like what a white dwarf is. It's the leftover core of a star that is no longer doing nuclear fusion. It's just emitting its energy. And it will continue to do that for trillions of years until it's got no more energy to emit out. And it'll be kind of like that black piece of coal that is in the bottom of your campfire that is totally cooled off and is no longer glowing. And again, we believe that'll take trillions of years to happen. The universe isn't trillions of years old yet, so we currently don't have any black dwarfs in the universe. We're just theorizing what will happen to the white dwarfs that are out there. Good? Okay. We are going to be working on, and I know this says period 3, but I put their capture question in your area, so I apologize. We today are going to be working on a handout that I put on your desk. I'm going to go ahead and bring that handout up. It looks like this. It is stellar evolution. And there is went into the wrong one. So I will go back here and go to stellar evolution here. All right, notice that there is a website. If you could please open up your computer and go to this website, www.phschool.com. I have written it over on that side of the board so that you can see it. And then there is a web code that you are going to need. So I'm going to go ahead and go to mine. I'm going to type in www.phschool.com. It will bring me here. And then I will see that I need a web code. So I'm going to put the web code CZP. And then in this box, I think it was 7252, enter, and it will bring me here. All right. So we're going to be going through an animated process. It says we're going to select the indicated mass of a main sequence star. Okay, I'm looking at these instructions right here. And then we are going to watch it evolve or change over time. So do we see where it says start on your screen? Please hit the start button. We're going to walk through the first one kind of together. So start. All right, and we're going to go through the introduction. Notice in this, it's showing us, a nebula, giant cloud of gas and dust, and then it's going to be a protostar. So we're going to read this introduction together, okay? And then we'll walk through it just so that you understand what to do and you're getting the information. It says, although stars are not alive, they evolve through a predictable life cycle. As a star begins its life as a protostar, protostar is not a real star yet. Has anybody ever heard of the idea of a prototype in the design process? Okay, prototype is what we start with. It's our idea, but it's not the actual finished model. It's just a prototype of what we want the finished model to look like. A protostar is not a star because no nuclear fusion has started yet. It's just a ball of glowing hot gas, not a star yet. So a star begins its life as a protostar in a nebula. Nebula is that giant cloud of dust and gases. How long a star lives and how it dies depends on how much mass it has. We're going to click on the protostar, and it's going to walk us through a process we're just going to look at. Oh, sorry, not yet. So then it brings us here. And notice up here at the top, it's got different sections. We've got low mass star right down here. And then we can change it using this little drag thing. I can drag it all the way up to a very massive main sequence star. So I'm going to go ahead and find middle ground. And I'm going to start with a medium mass or low mass star. I want you to start with medium or low mass because that's what the front page of this paper is asking us to start with. And it says that right here in the black area. So then once you see that, at the top, we've got some words to read. Stars are born in giant clouds of dust and gas called nebulas. In a nebula, gravity pulls the dust and gas together to form a protostar. Not a star yet, just a protostar. Over about 1 million years, the cloud continues to contract, meaning pull together, until a large amount of gas is compressed into a relatively small area. Now, it's important to note at this time, not one star is made out of one nebula. A nebula cloud is what's called a stellar nursery, meaning many thousands of stars can be made out of one cloud. The immense pressure raises the temperature in the cloud until nuclear fusion starts. Once nuclear fusion starts, now we have a true star, a star is born. How the star lives out its life cycle depends on the mass of the star. Our sun has a mass of 1 solar mass and will live about 10 billion years. Stars with more mass go through their life cycles more quickly than stars with less mass. The most massive stars complete their life in about only 10 million years, so very different than our 10 billion years. They will come to a violent end. We're going to use the slider to change the mass of the star. We did. When you are finished, you are going to go ahead and click the play button. You're going to watch what a medium star does. You can pause it if you want. I'm going to pause it because at the top it'll explain then what happens during a red giant stage. I'm going to pause it again, and then it'll show you the planetary nebula, and it'll tell you what happens during that stage, and then continues on. So I'm going to drag this back. I want you to spend about, do you think 6 minutes would be enough? Because after you go through this, you're going to press where it says test your knowledge, and you are going to then drag and drop some vocabulary into the right area. Once you get it correct, you're going to then fill this sheet out with the correct area. So I'm going to be quiet. I'm going to put about 5 minutes on the clock. You walk yourself through that, and then we'll come back. Those of you watching, you can go ahead and fast forward through this next section until we talk again. All right, 5 minutes are on the clock. If you need help or you're not sure what to do, ask me. You're just pushing play. Going through the process. Watch it as many times as you want, and then click on the test your knowledge. Once you're done, flip it over and do the backside with the high mast main sequence star. You'll have to reset it and then do the high mast star.
On which one? That?
The back. So when you're finished with the front, flip it over into the back. You'll have to then reset, if I can find it. You'll have to then, when you're finished filling it in, hit the reset button. It'll bring you back to where we were, and then you'll have to choose a high mass star. Here, I'll do this. And then you'll hit this reset button, and you'll go back and pick high mass star. put one more minute on because I know some of us are starting the next part. We'll give ourselves just a little bit of extra time. Just let it watch it. Just watch it all the way through. What do you think about it? Ah. We'll go over it in just a minute then. All right. Don't want to scare anybody. Let's go ahead and go over the first side on our low to medium mass stars. If you're still working, you still work. So then we have all stars are starting with this nebula. And a nebula is a huge cloud, and let's write that here. It is a huge cloud of dust and gases. This is evidence that past stars have exploded. All of this is filled with, it's just all different kinds of elements. And stars have exploded out or collapsed, and all of the elements that were fused inside of a star are now just floating around in this giant cloud. You can have little bits of gold and iron and everything, just elements floating around. After it starts, portions of it start to collapse. What do we call this right here? It's not a real star yet. What is it? It's a protostar. Once nuclear fusion starts, okay, so fusion is going to be starting. Once fusion starts, then it becomes a main sequence star. And it spends most of its life there. After the main sequence, Blake, this one's for you. What comes next in a low to medium mass star? Red giant. After a red giant, then it collapses in on itself and you get this beautiful formation. Sam, what is this formation? Yeah, it's called a planetary nebula because it looks like a planet. Planetary nebula. Nebula means gas cloud. So it's a gas cloud that is in the form of a planet because at one time there was a star there. All that's left now is all the gases that are surrounding the core. That star has collapsed. This is what's going to happen to our star. It's collapsed and all the gases just kind of float away, and in the center is the core. That core then becomes a white dwarf. Eventually it will cool over trillions of years and it becomes a black dwarf. Questions on that? And then the back is the same thing. You just do the same thing, you repeat. Good? Fantastic. We're going to take some notes on that. We're going to practice by taking some notes. So I'm going to come over here. I believe this was my note sheet. Nope. We're going to go here. This is going to be my note sheet. Here we go. You are going to have a homework assignment at the top of the note sheet, which I'm about to give you. I'm hoping that we'll have time at the end of class to work on it. But if not, somewhere on your note sheet, could you please write for class period 4, your EdPuzzle code. This is going to be the EdPuzzle code that you're going to have. I will show you where to find that on Canvas as well. Yes, sir. Absolutely. The conclusion on the back, Liz had a really good question. She said, should we do the conclusion? Yes, you should. I am not going to walk you through that, but if you look at the conclusion on the back, it says, look at the list of life stages above. How is the outcome for a medium mass star like our sun different from a high mass star like Betelgeuse? So I'm asking you, what's going to happen to our sun compared to a higher mass star? And then why is that outcome different? Why is it some stars end one way and another star ends another way? So do I want you to do that? Yes. Am I giving you time at this particular moment to do that? No. I'm going to take some notes with you. But yes, that is an important thing that you need to go ahead and process. Okay? If you look, one side is high mass, the other side is low mass. Why is it that, stars come out differently? Well, I've just kind of told you. The difference is all the mass. Different stars have different life cycles because of the different masses that they have. That's what's happening. Okay, let's go ahead and look at these notes. For our note session, we are going to have a question that is going to be our focus. And our question is going to be on this one. It used to be how do stars change over time, but I want it to be more focused on our sun specifically compared to other stars. So how about we say something like, why does our sun evolve differently than other stars? Why does our sun evolve differently than other stars? I'm going to move this up just a little. So every single star in the life of a star has to start with ingredients to build that star. Could you all shark your computers? I'd appreciate it if you'd shark them because we're not going to use them right now. We're going to use them at the end for our EdPuzzle, but just save the battery for now. All of these stars start with a nebula. A nebula is a huge cloud of dust and gases. Now, these can be several thousands or hundreds of thousands of light years across. Big, massive clouds of dust and gas that have come together with gravity. The more mass you have, the more gravitational pull you have, and so these clouds can be very massive. Out of these clouds, we get stars. These are called stellar, meaning star, nurseries, meaning babies. So this is where baby stars are born. Thousands of stars can be born in these gas clouds. So we're going to put the word gravity right here. And I'm going to put an arrow to this arrow. This is gravity pulling parts of the cloud, pockets of the cloud together. Gravity. And then this becomes a protostar. So we're going to write the word protostar. I think I'm going to change my pen color to maybe a blue so it'll show up just a little bit better. Protostar. But it is not a star yet. Not until what happens? Good. So then let's go ahead and write nuclear, or how about this? Fusion begins. Fusion starts. And I'm going to put an arrow here, and I'm going to put an arrow here. The moment nuclear fusion begins, we have a star. And now we see two different ways or two different routes that can happen. On one side, we're going to go through our low to medium mass stars. On the other side, we're going to go through our high mass stars. So let's go ahead and start with medium mass over on this side. Whoops. So I'm going to try to write sideways and say this is going to be our medium mass evolution. That was difficult for me to write like that. On the other side is going to be our high massed star evolution. So I'm going to write high mass evolution. That was difficult. Okay. After fusion starts, we're going to put a little dot here. So watch where I'm putting our dot. We're going to put dot, 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 dot underneath fusion starts. We're going to go ahead and separate these into different stages of life. So after fusion begins, the star enters what's called the main sequence stage of its life. Main sequence stage. In this stage, you have your stars in the fusion cycle of hydrogen plus a hydrogen equals a helium. This is their hydrogen fusion stage. This is where they spend most of their life. So I'm going to put longest stage. This is where they spend most of their life, is on this main sequence. Burning hydrogen and hydrogen into helium. Okay, we're going to put another dotted line here, and I'll separate the rest of the dotted lines so that you know how much space you have to work with. So this is going to be another dotted line. That's going to start another stage. And then in this location, we're going to put another dotted line. That'll be another stage. So we're just going to separate them by dots right now so that you know how much space you're going to need. Then underneath here, we're going to put another dotted line through here. So that's going to be kind of how we're going to separate those stages of life. So main sequence is kind of its longest stage. After that, it's going to transition into old age. Old age. Mrs. McGrain's transitioning into old age. This is where it is now going to start fusing other elements like helium plus helium into something like carbon. Okay, so it's no longer just fusing hydrogen. The next stage after old age is death. This is the death stage. Then the final stage is the remnants or the leftovers, what's left after death. So I'm going to say leftovers or remnants, whatever you want. Those are the leftovers. So now we're going to go through each stage, looking at a medium mass star and then looking at a high massed star. So let's start with the star that's most like us, which is the sun. This medium mass evolution is going to live a lot longer because there's less mass. Remember, small mass stars live long lives. So I'm going to say live longer. And I'm going to put an arrow from medium mass evolution up to live longer. And I'm going to put from live longer an arrow down to this first circle right here so we know we're talking about this one. So these stars are like our sun. I'm going to write a sun-like star. So sun-like star. So these are stars like our sun. Our sun is a medium-massed star. So low to medium-mass stars are going to evolve through their life like this, spending most of their life on the main sequence where they are going to be fusing hydrogen and hydrogen into helium. Then when they transition into old age, they will reach giant stage. They will swell up and become giants. They will not be fusing hydrogen into hydrogen anymore. Yep. It is, some of them will be red, but not every single one will be red, but our sun definitely. If we want to put red, we could put red. You want to put a red there, you put red there. You'll get confused. No, we can put red giant. Absolutely. It's either, it can be a red giant. That's definitely what our sun is going to be. You're right on with that one. After the red giant stage, it's going to die, and it is not going to explode into a beautiful supernova. It's going to collapse into just what's called a planetary nebula. Now, this nebula is going to be a cloud, so I'm going to try to make this look a little bit more cloud-like. And in the center is going to be the core. So I'm just going to write planetary nebula. The center is the core, and the rest is just going to kind of be a ring of gases and elements just floating around. During this stage, in this nebula cloud, we're going to put an arrow, and we're going to put that out of this cloud. You're going to have the elements that are going to be given off are going to be elements of hydrogen all the way to oxygen. So I'm going to say give off, and I'm going to write element H all the way through O, hydrogen to oxygen. That's what these low mass stars, low to medium mass stars are generating through their lifetime. So when it collapses, you're going to have just a cloud, a halo, if you will, of elements of hydrogen all the way to oxygen. All right. Eventually, bless you, eventually those gases are going to just float away, and you're going to be left with the center, which is going to be the white dwarf. It's a white dwarf star, and this will continue cooling off for trillions of years until eventually it will become a black dwarf. And again, we've not actually ever seen a black dwarf star. We just theorize that it will be out there after the white dwarf cools for trillions of years, because the universe is only 13 billion years old. So we've not had time yet to allow white dwarfs to cool into black dwarfs. And they'll just be this chunk of, element floating around. Awesome. That is going to be what our sun and low mass stars are going to do. Let's go ahead and look at our high mass stars. These are much more exciting. These are going to have short lives. These are going to evolve over millions of years, not billions of years. So let's go ahead and write that these are our large mass stars. And again, they're going to spend most of their life in the main sequence, except not billions of years, only millions of years in the main sequence. Before they start transitioning into old age, and they don't become a red giant, they're going to become a red super giant. So these are going to be our super giant stars. Much more massive stars are going to become much bigger super giant stars. And again, in this stage, they're no longer fusing hydrogen and hydrogen. They have transitioned into fusing other elements. Okay, here's where it gets exciting. This is when they die. When they die, supergiants go supernova. So this is a supernova. They explode. They go boom. I should put that in the supergiant stage, they can fuse up to iron. Iron is Fe. So they can fuse up to iron in the supergiant stage. So how do we get elements that are heavier than iron? The star has to literally blow up in order to make gold, like my wedding band is. So because I have this gold wedding band, that's evidence that a star has exploded in a supernova. Because the only way that there's enough pressure and heat to make an element like gold or uranium or silver is to have a star end its life in a big explosion. At that moment in time, there's enough energy and pressure to create the other elements. So during the supernova, it will create elements from cobalt all the way to uranium. This is when those elements are created. That includes gold, platinum, all of those precious metals. They have to be created when a star blows up in death. So thank you, star, for giving your life for my beautiful wedding band. Then what's left over is either going to be a neutron star. This means that that core has collapsed in on itself and become so dense that it's an incredibly dense star. They say that a teaspoon of a neutron star would have as much like density or enough mass like the a city of Chicago. So it's just very, very dense. And then it stops. It doesn't collapse anymore. Now, if it's more massive, it's going to continue collapsing in on itself, literally turning the fabric of space and time inside out as it collapses, and it creates a black hole. And this is kind of like, it reminds me of like a bathtub that drains, and everything, just kind of spins around it and drains inside of it. And where it goes, who knows? Maybe black holes are just rips through fabric of space-time and are like dumping into other, universes, other dimensions of time. We don't know because we can't get into a black hole. It's a one-way trip. That's for sure. All right. So that's the note section. And I videotaped this so that you can go home and watch it. You have enough information now to answer the questions on the side and the summary on the bottom. So you have enough to do that. What I'd like to do now, Aisha, how much time do I have left? About 6 minutes. So let's go ahead and open our computers and go to our EdPuzzle to make sure that you are comfortable getting into the EdPuzzle. Beg pardon? Great. So then you have 6 minutes to work on it. So if we go to Canvas and you click on where it says EdPuzzle Evolution of a Star, then there is your code for 4th hour. It looks like it says Anu Ruth. I'll spell it for you. I'll write it right here. So all of my people at home that are watching this, all of your codes are listed right here. And I will post the notes for Stellar Evolution by the end of the day. So that's what you're going to be working on for the remainder of class.